Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today. If you've ever felt that intense anticipation as a roller coaster slowly clanks up to the very top of a massive hill, or if you felt the wind rush past your face as you just coast down a hill on your bike, well, you've already experienced the exact stuff we're diving into today. We are unlocking the secrets of mechanical energy. Basically, we're going to break down the invisible rules that govern how things move around, how they crash into each other, and really, how things just get done in our physical world.
So, to get our gears turning right off the bat, I want you to picture a super simple everyday action. Think about it. How does a hammer actually drive a nail? I mean, it seems completely obvious, right? You swing the heavy hammer, it hits the little nail, the nail goes straight into the wood. Easy. But what are the invisible forces that are actually making that happen? How does the simple swinging motion of your arm somehow transfer enough power into a solid piece of steel to shove it deep into a thick piece of wood? Hold on to that image for a second, because by the end of this explainer, you are going to see that simple, everyday action completely differently, through the eyes of a physicist.
All right, let's jump right into Section 1, the energy of action.
Okay, let's nail down exactly what we're looking at here. Mechanical energy is, at its core, the sum of an object's kinetic and potential energy. It's totally tied to how something is moving or where it's positioned. But honestly, the absolute most important phrase I want you to remember from this entire explainer, like our absolute mantra for today, is right there in the definition. It is the ability to do work. If an object has mechanical energy, whether that's because of where it's sitting or how incredibly fast it's moving, it has the ability to do work. Seriously, repeat that in your head with me. The ability to do work.
But wait a second, what does doing work actually mean in this context? Because in physics, doing work absolutely does not mean sitting at your kitchen table doing a math worksheet, not at all. Doing work simply means using energy to apply a force to another object in order to displace it. And displace is really just a fancy science word for forcing something to move from its original spot, its mean position. So if you apply a force to something and physically cause it to move from point A to point B, congratulations, you have just done work. Mechanical energy is basically the fuel that allows a body to apply that exact force and make that displacement happen. It's all about position and motion.
Moving right along to Section 2, two sides of the coin.
So here's the cool thing. Mechanical energy isn't just one single boring thing. It actually comes in two totally distinct flavors. First up, we've got kinetic energy. You can think of this as the energy of pure motion. Literally, if something is moving, it has kinetic energy. Simple as that. Then on the flip side, we have potential energy. This is stored energy. It all depends on an object's position. It's energy that is just sitting there, waiting to be unleashed. Together, these two act like a tag team. Total mechanical energy can be made up of just one of these or a combo of both.
Let's anchor these kind of abstract concepts to the real world for a second. Think about a car just zooming down the highway. Because it is actively, visibly moving, it possesses mechanical energy in the form of kinetic energy, fast and active. Now, imagine picking up a really heavy object, like a bowling ball, and lifting it high above your head. Even if you are holding it completely, perfectly still, it still possesses mechanical energy. Crazy, right? But why? Well, because of its vertical position way up above the ground. Gravity desperately wants to pull that thing down. That high up position gives it stored energy, which is our potential energy. So both the speeding car and the hovering, totally still object have mechanical energy, just in very different forms.
Which brings us to Section 3, putting energy to work.
Okay, so the absolutely crucial point here is how an object actually harnesses this mechanical energy we're talking about to cause another object to be displaced. Imagine a massive collision. A super fast-moving object just crashes head-on into a completely stationary object. What actually happens in that split second? Well, during that crash, the mechanical energy of the moving object is suddenly harnessed to apply a massive physical force. And that newly applied force is going to cause that totally stationary object to suddenly jolt and move in the exact direction of the exerted force. It's just energy being transferred directly from one object to the other, doing actual physical work in the process.
And boom, that brings us right back to our opening question. A hammer is, at the end of the day, just a tool we designed to utilize mechanical energy to do work for us. Let's look at the steps. Step 1. As you swing your arm, the hammer gains mechanical energy in the form of kinetic energy. It's in motion. Step 2. Smack. The fast-moving hammer hits the completely stationary nail. Step 3. Because that hammer came in with all that kinetic energy, it possessed the ability to do work. So it instantly applies a massive force to the nail, displaces it, and drives it deep into the wood. Boom, mystery solved. It is literally just kinetic energy transferring straight into physical work.
All right, time to level up. Section 4, the math behind the magic.
Now, as I mentioned a bit earlier, the mechanical energy of a whole system can be from its motion, its stored position, or both of them working together. Because of that, calculating the total amount of mechanical energy is actually incredibly straightforward. You literally just take the two sides of our coin and add them together. That's it. Total mechanical energy simply equals potential energy plus kinetic energy. Let's take a quick peek at the specific formulas scientists use to figure this out. And hey, do not let the letters intimidate you. They are literally just abbreviations. For potential energy, or PE, the formula is mgh. That just stands for mass times gravity times height, which makes perfect sense, right? A heavier object that's lifted way higher up is naturally going to have more stored energy. Then for kinetic energy, or KE, the formula is 1/2 of the mass times the velocity squared. Again, perfectly logical when you think about it. The heavier something is, and the faster it's moving, the more active energy of motion it has.
And that, my friends, brings us to our grand finale equation. If we want to find the total mechanical energy of absolutely any system, we just take our formula for potential energy, mgh, and we add it straight to our formula for kinetic energy, 1/2 mv squared. Total me equals mgh plus 1/2 mv squared. Once you know these two totally simple parts, you literally hold the key to calculating the total energy of moving and resting objects across the entire physical universe. How cool is that?
Which leaves us with one final thought for today. We've defined exactly what mechanical energy is, we've seen how kinetic and potential energy team up to do actual physical work, and we've even conquered the math behind it all. So here's my challenge to you. I want you to look around the room you are sitting in right now. Seriously, look around. Where's mechanical energy hiding? Is it in a heavy textbook sitting way up high on a shelf, just full of potential energy? Or maybe it's in a spinning ceiling fan above you, packed with kinetic energy. The invisible rules of physics are operating all around you, every single second of the day, just waiting to do work. Keep your eyes open, stay curious out there, and thank you so much for joining me for this explainer.